Swayam Prabha. Digital India. Educated India.
Welcome everyone for our online NPTEL course Environmental Chemistry and Microbiology. This course will be taught by Professor Sudha Goel and myself, Professor Anjali Pal. We are both from the Civil Engineering Department of IIT Kharagpur. We have divided this course into two parts. The first part will be environmental chemistry, that will be covered by me, and the second part will be environmental microbiology, that will be taught by Professor Sudha Goel. So, in my module 3, I will talk about the chemical kinetics. In my first module, I already told about the acids, bases, and in my second module, I have covered the chemical equilibrium. This is my third module and I will talk here about the chemical kinetics. Now, chemical kinetics, you all know, chemical reactions, you know that there are some reactants that react to form some products, and in this lecture, this is my 12th lecture, and in this lecture under chemical kinetics, I will cover the rate of a reaction, the order of a reaction, molecularity of a reaction, and determination of order by using differential rate law. So, to talk about the chemical kinetics, let us start a very simple example. Say for example, A is a reactant which is giving a single reactant A is giving to a single product P, then rate and order of a reaction is very important, and actually the reactions we can think about in two different ways. We can describe the reaction in two different, we can classify the chemical reaction in two different ways. The first is the molecularity of a reaction, that means considering the number of molecules that must react to form the reaction product, that is the molecularity. Okay. And then the second one is the in terms of the reaction order. So, we have to remember that molecularity of reaction we can tell from the balanced equation, that is that just now I told that number of molecules that are reacting from there. So, in terms of molecularity, there may be unimolecular reaction, there may be bimolecular reaction, there may be termolecular reaction, but in terms of reaction order, this order has to be determined by experiment. We cannot just directly from seeing a balanced reaction, balanced equation, we cannot tell that the order of the sometimes order of the reaction is 2 or 1 or 0. Sometimes the molecularity and order may match, may be the same, but not necessarily it will be the same, it may be different also. That is a very important concept for chemical kinetics. Now, for which type of reactions we should determine the order. Okay. There are three types of reactions. First thing is the irreversible reaction. Irreversible and reversible reaction I already discussed in the chemical equilibrium chapter, and so order we can determine for the irreversible reactions. or order we can determine in the initial stages of most reversible reactions. Means there are many reactions, they are actually all reactions are reversible reactions, but those reactions which go far to the right, we can tell that okay, this is irreversible reaction. Now, many reactions are reversible reactions. For those reactions also we can determine the order in the initial stages, okay, initial phase of the reaction, beginning of the reaction, okay, we can determine the order. Now, for reversible reactions where the position of equilibrium, this is another case, in case of reversible reaction where the position of equilibrium lies far to the right. This concept I have already given in the equilibrium when I was discussing the equilibrium. So, far to the right means it is almost going to the completion. In that case also we can determine the order of the reaction. Now, what is the order of the reaction that we must know? Okay. So, we have already got some idea about the rate. Say for example, this is a very simple reaction, A is giving to P. So, rate of disappearance of A, that is the rate of the reaction we can consider, that means we are considering the reactant A. So, how A is disappearing, that is also we can tell that rate of the reaction, isn't it. So, it can be, because it is the reactant, so minus sign should be applied. So, minus dCA dt, this is the rate, and so rate is related to the concentration in some way. How it is? Rate is the nothing but K, it is the proportionality constant into Ca. Ca, you know that concentration can be expressed in two different ways. This is one way to represent. So, concentration of A is the subscript. Another way we can represent the concentration, that is within the third bracket. Okay. So, rate of reaction, rate of disappearance of A is nothing but K into Ca to the power n. So, what is K and what is n and what is Ca? Ca is the concentration of A at a particular time, at time t, say for example, and n is the order of the reaction, and K is a constant which is called the specific rate constant, or it also called rate constant. So, this is something like the, you know that the equilibrium constant. So, equilibrium constant does not depend on the concentration, that we have already learned. This is also does not depend on the concentration. It depends on the temperature, but it does not depend on the concentration. And depending on the order of the reaction, the unit will change. The unit of K will change, but the unit of rate is the same. This is nothing but the change of concentration per unit time. So, it is the if you express the concentration in terms of moles per liter, say for example, and times a second, then it will be moles per liter per second. Or if you express the time in terms of hour, then moles per liter per hour. If you express the concentration in terms of milligram per liter, then it will be milligram per liter per second or per hour. So, rate will be the same means irrespective of the first order or 0 order or second order reactions. Now, here you can see that if you, this is the rate expression, it is called rate equation or rate expression. Okay. Now, if you take the logarithm in both sides, then what you will get? You will get log dCA by dt is equals to log K plus n log Ca, log K plus n log Ca. Or you can write that in this way you can express, or otherwise this concentration term you can write in this way also. That just now I have explained this. Now, if by experiment you can determine this value log dA by dt, log minus dA by dt, minus is because it is the reagent. So, if you can determine experimentally these values and log A, then at different concentrations of A, then if you plot log A in the x axis and in the y axis log minus dA by dt, then depending on the order of the reaction you will get these curves. It is the equation of a straight line. So, you will get straight line curves, but the slope will be different. In case of second order reaction, because this is 2, so you will get slope 2. In case of first order reaction, you will get the slope 1, and in case of zero order reaction, you will get a straight line which is parallel to the x axis. So, so it is possible to determine the order in this way. And you also need to know that order, because it is some value you are obtaining from the experiment. So, it may be either integer or it may be fraction also. Say for example, it can be 1.5, it can be 0.5 also. So, order can be fraction also. Say for example, acetaldehyde decomposition. So, decomposition of acetaldehyde at 450 K. So, at high temperature you will see that the order is 1.5. This is possible, but sometimes in practical purpose, say for example, if you see the slope is like 0.95, then you can think that okay, it is 1, it is close to 1. So, you can tell that okay, order is 1. So, it is first order reaction. Now, so it is understandable that from the concept of instantaneous rate, this is the minus dc dt. Here you know that it is the slope at a particular point, and the time difference is very small. So, to determine the instantaneous rate, you understand from your common sense that it is difficult. Okay, it is very difficult to determine the instantaneous rate. So, how then you will get the order of the reaction? By using the previous expression. Okay. So, Swinburne, you know, Swinburne in 1971, he developed two different methods. One is the order with respect to time, and the other is order with respect to concentration. There are two methods developed by him, and by these two methods the order can be determined easily. So, what is his assumption is that he assumed that at the midpoint of the time interval delta t, dc dt you can think that it is same as delta c by delta t. So, this is his assumption. Okay. And then the c, you know, c is the midpoint, and c, it is the c average is the midpoint of the concentration interval delta c. Okay. So, if you assume this thing, then you can say that log delta c by delta t is same as log k is equal to log k plus n log c average. So, this is the same expression, but this is his assumption that this is the midpoint of this delta c, and this is instead of dCA dt, he assumed that delta Ca by delta t. Okay. So, this is easy to understand. Okay. Now, if the reactant concentrations, now how the experiment will be? So, you do some reaction. So, for example, you do some reaction and the reactant concentrations are measured experimentally. okay, at different time intervals. I will show some example, then it will be more clear. So, at different time intervals you measure the concentrations experimentally, this is easy. And then the reaction order can be determined from the slope of the straight line obtained by plotting delta Ca by delta T versus log Ca, this is average. So, that way you will get the order of the reaction, okay. After plotting this versus this, you will get the order of the reaction, okay. And this order, he said that it is order with respect to time. Now, let us see with some example, okay. How is the example, okay. Here you can see that this is the experiment, okay. This is the experiment that is done with some batch, in some batch reactor, okay, you know, some batch reactor, okay. And this is the time in minute, okay, 20, 32, 41 and this is 50. So, time different time, at different times you are taking some aliquot and then measuring the concentration of the reactant, that concentration you term as Ca, okay. Now, then you have to make some table to show the data. This is the time column. So, these are the times that you are getting from here, and this is the Ca, these are the Ca values, okay. So, delta Ca, what it will be? It will be the average of this, means midpoint of this. So, this is this one, okay, and midpoint of this, and then means not midpoint, this is the difference, okay. This is the difference of this one, this is the difference of this one, and this is the difference of this one. Then delta T is the difference of this one, this difference of this one, difference of this one. So, that is why it is written in the middle, okay. Now, so you got delta Ca values and delta T values. Now, you have to calculate delta Ca by delta T, okay. In this column you have calculated this value, and this is the average. So, what is the average? This one plus this one by 2, this one plus this one by 2, like this, okay. So, this is the Ca average, actually average means midpoint, okay. And now, once you have all this data, then you can calculate, you can find out the log values. So, log minus delta Ca by delta T, and this is log Ca average, okay. And then you have these values and these values. Now, you have to plot log delta Ca by delta T, obviously minus, I am not mentioning all the time, this one and log Ca. So, the curve you should get, I have not shown you the curve how it will be, you can do it, this is an example, means exercise, you can do it and you can plot it, and you can see how you are getting the n value, that is the order of the reaction, okay. So, this is one way of doing by using the differential rate law to get the order. Now, the other method he has explained, the same person Swinburne 1971, this is the order with respect to concentration. Now, what he has done here, that the experiment is carried out with several minimum 4 runs, because to get a straight line we need minimum some points, that is why minimum 4 runs are done. What he has varied? He has varied the initial concentrations. So, starting concentration, initial concentration he has varied. So, 4 different experiments with different initial concentrations of A, okay. And then these concentrations are considered as the concentration at 0 time, okay. Now, the reaction starts. So, when the reaction, we have 4 experimental setup, and then reaction starts, and then just small interval has been taken, say 1 minute is taken, and then the concentration of A is measured for the 4 runs, okay. Then the delta Ca means the concentration difference, say 0 minute and 1 minute, that we can easily find out, and delta T here we have taken 1 minute. So, delta T is 1. So, this this value we can get, and we can get also the log of this, and then log Ca. This is the initial concentration, that is why 0 term is coming, here also 0 term is coming. Ca0 is nothing but the initial concentration. Okay. So, log Ca0 we can easily calculate, and then we have to plot log minus delta Ca by delta T 0 is plotted versus delta Ca. Okay. So, here also we have to see that what is the slope of the straight line. So, once the slope is known, then we can find out the order of the reaction from the linear plot. Okay. So, reaction order determined by this method is termed as order with respect to concentration. These two are very nice methods. Okay. Now, to understand this one, there is some, you can see this data from the experiment that has been done with 4 runs. Okay. So, time, here is the time. So, 0 minute means initial concentration, then 1 minute. So, just after 1 minute the concentrations are measured. So, this is the 0 time concentration, this is the at 1 minute what is the concentration. There are run 1, run 2, run 3 and run 4, and then you have to put it in a table. So, there are runs, 4 runs, so 1 run, first run, second run, third run, fourth run, and then here the calculated values 5.4. So, this is the difference delta Ca, delta T is 1 here. So, the difference by 1. So, difference is 5.4 here. In this case it is 8.8, in this case 12.6 and 17.8 here. So, you get this value, then you have to take the log of this value, that is nothing but this one, then log Ca, this is the initial concentration. So, log value of the initial concentrations, these are the. So, you have to plot these values against these values, and then you have to see that what is the slope of the straight line. Then you can easily find out the order of the reaction. This is the some method that differential rate law, using differential rate law you can determine the order of the reaction. Okay. That means instantaneous rate, you are just converting it into delta terms, means the time period you are increasing, and in the first case you are taking the midpoint as the concentration, two different concentrations you are taking the midpoint, that is the average concentration, and here in this case you are taking the initial part, very short time period you are considering, and that is the order with respect to concentration. So, this in this lecture what have been covered, you can read from the same 2 books that I mentioned in my previous lecture, that is under chemical kinetics. The same 2 books you can read to get more elaborative way you can get the concept. Thank you very much for your kind patience.